Hi guys, welcome back to Data Every Day. Today we're looking at a data set of fetal health. Um, so I don't think the preview is loading, but basically it's a data set of different fetuses, and we're going to try to classify the health of a given fetus as normal, suspect, or pathological. And we're going to use Optuna to find the optimal hyperparameters for our models. So this is my first time using Optuna, and I think it's an awesome library. So let's get right into it. I have a few imports we're using: NumPy, Pandas, Matplotlib, .pyplot, and Seaborn. And then for pre-processing, we're going to use standard scalar and train test split. Not too much pre-processing today. It's a pretty simple data set, nice and clean. But then we're going to actually not. This is wrong. This would be logistic regression. We're using Optuna, logistic regression, and we're going to use TensorFlow to build a neural network, and we'll use Optuna to tune the hyperparameters for both logistic regression and our neural network. And I'm just turning off warnings here. So let's go ahead and import that. And we can load in the data using pandas.readcsv. We'll get the file path right over here, fetalhealth.csv. Paste that in, take a look. So, like I said, it's a very clean data set. You can see we can't see all the columns. So I'm going to go into the console and type pandas.setOption max columns none. And that will give us access to all the columns. But as you can see, they're all numeric form. If I get some information about the data set, you can see everything is float values, and there's also no null values. Right? So that's fantastic. That means all we have to do to really process this data set is scale it. So I'm going to check the fetal health column. That's what we're trying to predict. And I want to see the unique values in it. And it actually it actually goes 1, 2, and 3 as the unique values. That's all the way at the end here. We have 1, 2, and 3 in this column. But TensorFlow actually requires that the classes start from 0. So all I'm going to do is take this column and subtract 1 from it. And if I do that, you can see now the unique values are 0, 1, 2. So that's how we want that. All right, let's also let's visualize the correlations between the variables. So we can do this by creating a new. Well, we can create a correlation matrix using pandas. It's a data.core. It's a pandas function that will generate the correlation matrix for each variable in the dataset. And we can create a new new pyplot figure. Let's give it a fig size of 18 by 15. And then we'll use Seaborn to create a heat map of the correlations. I'm just going to turn on annotations and set the minimum correlation value as -1. Alright, let's show that. And as you can see, there are actually a few values in here with extremely high correlations, namely this -0.9, and then these right here, this 0.93. All these are about 0.9. So anything that's like near 0.9, I'm going to try to drop redundant features that way. Because, for example, this mean, right? It's so heavily correlated with both the median and with the mode that they're essentially all saying the same thing. So what I'm going to do is just to avoid having such redundant features, I'm going to drop 2 of them. I'm going to keep the mean, drop the mode and median. And then over here you can see histogram width and histogram min are very strongly correlated as well, this time negative correlation. So we're going to drop one of those as well. So I think we'll drop histogram min, histogram mode, and histogram median. So data equals data.drop histogram min histogram mode and histogram median. Alright, and we're dropping it from axis 1. And so now we should be ready to scale. So splitting / scaling. So we're going to split it into x and y. Y is what we're trying to predict, and that's just going to be the fetal health column at the end here. You can see no one feature has tremendous predictive power in fetal health. It's going to be a combination of the features that gives us our predictions. So we'll make a copy of that, and then for x, we'll just drop fetal health. So it's everything except the fetal health column. And I'll make a copy of that as well. Alright, now we'll create a scalar object. This will be a standard scalar from sklearn. This will give each column a mean 0 and unit variance. So x is going to be scalar.fit transform x. Alright, and last thing I'm going to do is split it into a train and test set using the train test split function from sklearn. So we're splitting x and y, so we have x train, x test, y train, y test equals train test split x, y, and we'll give a train size of 70%. Alright. Okay, let us first optimize. So I'm going to write this: optimizing regularization strength for logistic regression. So we're actually going to optimize the inverse regularization strength, which is the C value in sklearn's logistic regression model. And the way we're going to do this is we're going to create a function that we want to optimize. And the function here is going to give us the loss of the model with a given hyperparameter. So I'm going to call it, the way Optuna works is really cool. We can create this function. It can be anything, but we'll call it getResults. And we pass in a trial. And this is an Optuna object that's going to get passed in here. We're going to start by creating our hyperparameter, C. And we're going to tell Optuna trial.suggest log uniform. So what this is saying is we're going to give it, so I'll call it C, and we'll specify a min and max. So we're going to have a small regularization strength and a large regularization strength. And what it's going to do is, for each trial, it's going to draw from a log uniform distribution, or a reciprocal distribution, values between 0.00001 and 10,000. And the reason we use log here is because we want to draw more values near the smaller, since, how do I say it, like, because 0.0001 is a lot different from 0.001 or 0.01, but the difference between 1,000, 5,000, 10,000 is much less, if that makes sense. This is why we're using log instead of just regular uniform. But basically, this is saying, okay, so each trial is going to be a new random value from this distribution. And our model is going to be a logistic regression model with C equal to C. Then we'll fit it. So each time we're going to fit it. X train, Y train. And we'll return the score. So I said we were going to optimize the loss, but we're actually going to start by we're going to optimize the actual accuracy here. So X test, Y test. So model.score will return the accuracy value. And we're going to maximize the accuracy rather than minimize the loss, although it doesn't really matter too much. So we should be okay. If we were doing a regression problem, we'd certainly want to minimize the loss. Alright, so then what we do is we create a study from optuna.createStudy. And we'll specify the direction as maximize. And this is this is saying we're going to maximize something rather than minimize it. Then we will call study.optimize and we're going to pass in get results as the function we want to optimize. So we want to find the maximum of get results, which will be the maximum accuracy value. But we're going to pass in n trials is 100. So it's going to try with 100 different C values between this range. And it's going to try to find the maximum value of get results based on based on the values for C. And we'll just include show progress bar equals true. Alright, and so it's trying all these 100 different C values, and it's going to come up with some best parameters, and we can get that from study.bestparams. So I'll store this in best params, and then let's just take a look at it. So best C value it found was 0.2. So let's see how that goes. Let's create a new model, Logistic Regression, and we're going to specify C as best params sub C. Then we'll fit it, and we'll get the score. And we have a 90% accuracy. So pretty good. And as a test, let's see with the default C value, we actually get, okay, it's similar, but with best parameters, so this was a 90.4, this is 90.9. So there is an improvement there. Okay, so let's see if we can get better results using a neural network. So optimizing hidden layer sizes for a neural network. So let's just take a look at the shape of our input. Since we're using TensorFlow, we have to specify. And what I'm going to do is I'm going to generate the model inside a function. We can call it test model. So this will create the model with given hidden layer sizes. Let's call it A and B. This will be the sizes of our hidden layers. And it will basically create the model, compile it, fit it, and then return a loss value as a result. So let's also specify the batch size and epochs in here. I'm giving it a large number of epochs because I'm going to call it early stopping. So inputs is going to be a input layer from tf.keras, and the shape of our input is just going to be x.shape sub 1. So this value of 18 right here. Alright, then we'll create first hidden layer, hidden 1, tf.keras.layers.dense, and the size of this is going to be A. ReLU activation, and pass inputs in. Then we're going to create a second one with the size B, and we're going to pass in hidden 1. Then our outputs will be another dense layer with 3 activations, 1 for each class. Remember, we have 0, 1, and 2 as our health for the fetus. And this will have a softmax activation. Here we'll pass in hidden 2. Alright, then our model will be tf.keras.model, passing in inputs and outputs. We'll compile the model. We'll use an atom optimizer. For loss, we'll use sparse categorical cross entropy. And metrics, we'll just use accuracy. Alright, then we'll fit the model. We're going to pass in xtrain, ytrain. Let's give it a validation split of 20%. We'll include the batch size and epochs. We specified that in the parameters above. And then we'll include a callback function. So this will be tf.keras.callbacks.early stopping. And we're going to monitor the validation loss and we're going to stop after the validation loss does not improve for three epochs. So when this stops decreasing, we wait 3 epochs, and if it's still not decreasing, we're going to stop the training and restore the best weights, the weights from the best epoch. Alright, I'm just going to turn off verbose mode here. And at the end, we're going to return model.evaluate xtest, ytest. And I'll just turn off verbose mode here as well. Okay, so now this function sets up our model with 2 given hidden layer sizes, compiles it, fits it, and returns the results on the test set. So now we can create our get results function. It's going to take in a trial, and we're going to draw the hidden layer sizes, this time from a uniform distribution. So a equals trial.suggest uniform. So before we used suggest log uniform, but this time the hidden layer sizes, we don't really care about smaller values as much the way we did before. So we're using just a uniform distribution where every value is equally likely. And the minimum we'll use is 16. Anything below 16 usually is too simple. Maximum, let's make it 1024. Okay, and we'll do the same thing for B. Actually, we should specify this. We're going to call this one A. Call this B. And we're going to return test model, which is this function here, called on A and B. Right, so we're passing A and B like this, and we want to only get the loss value. So we'll say 0, because evaluate returns loss and accuracy. So we're just getting loss. And so this time, so I'll run that. This time we're going to create a study. So optuna.createStudy. And this time we're going to specify direction equals minimize. This time we're not going to maximize the value, but rather minimize it. And this is actually the default value, but I'm just leaving it in there so we can understand what's happening. Then we're going to call study.optimize. And so we're optimizing get results, which is this, with different A and B's each time, and we're going to have 100 trials. Let's also show the progress bar. Alright, we'll run that. And this one's going to take a little longer, so I will pause the video and come back when it's done. Alright, so we have finished, and now let's get the best parameters from the results. So best params equals study dot best params, and just take a look at them. So best value for A it found was 775. Best value for B is 25. Interesting that they're very different. It's sort of interesting to think of like the data, like more complex information, and then more like less information, and then finally just the 3 values. It sort of like converges down to a single set of results with these hidden layer sizes. Okay, but let's now test the model on best params sub A and best param sub B. So now we're going to test it with the optimal parameters to get the final result. And we end up with an accuracy of 91.4 or so. And that actually is an improvement from our 90.9 in the logistic regression case. So this will sum up today's video. Thank you so much for watching. I hope you enjoyed this brief tutorial on Optuna. So if you did enjoy the video, be sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. So I'll see you guys tomorrow. Have a fantastic day.